Hello, good morning. Let us continue with the lecture 17. So we were discussing moments, higher order moments, and also moment generating functions. So this is how we defined a central moment. The nth central moment about the mean will be denoted like this here, where mu n is expectance of x minus expectance of x and then whole to the n. So this is how we define the higher order moments. So here with different values of n, we will get moments such as expectations and then variance and so on. Okay. So zeroth central moment is denoted by mu zero. So continuing with this, and this is 1 because n0, then this becomes 1. The first central moment mu1 is 0, and so we should note that first central moment is not necessarily the expected value, okay, because this is x minus ex. So mu1 is expectance of x minus x, which will be 0 due to linearity of the expectation. Okay. But the first central moment, if you compute about origin, so this is, we are computing about the mean. So this is moment about mean. In other words, this is a central moment, and if we compute it about origin or 0, then it indeed becomes the first central moment, indeed becomes the expectation. The second central moment, which is denoted by mu2, is called variance, and it's denoted by sigma square. So second central moment is indeed the variance, and then we were asking, is there a quick way to generate moments? Okay, so is there a way that we can generate higher order moments in an easier way rather than computing this completely? So then we saw that there is something called a moment generating function here. It's denoted by mxt here. So the moment generating function is the expectation of e to the tx. Okay, so e to the tx is some random variable. Okay, function of some random variable where t is the parameter here. Okay, so if I take an expectation of gx, then we have defined before that expectation of gx will be etx times the PMF of the random variable x. So if we look into this term, then we saw that if we compute this, and moment generating function is a function of t. So here if I put t equals to 0, then I get 1. Okay, that's evident. And then if I have to compute the expectation value, then I take the derivative. So this means the derivative. And since this is a function of t, when I talk about derivative, then it must be a derivative with respect to t. Okay, so this is with respect to t. And then we compute this derivative at t equals to 0. Okay, so we first compute the derivative and then we substitute t equals to 0 there. So this is the derivative, and so let us see if we could compute moment generating functions. So for some of the distributions that we have seen, so let us say we have a discrete random variable whose PMF is given by binomial with parameters n and p. The moment generating function will be given like this. So here this is the PMF of the random variable x, and this is the etx that we have to multiply with to create a moment generating function. So if we simplify these things, okay, so if we simplify these things, then we get a moment generating function like this. Okay, so the idea here is that with this moment generating function, I can generate higher order moments. Okay, so if we differentiate this with respect to t, we get this. Okay, So now if we set t equals to 0 here, so if we put t equals to 0, then we find that that this comes out to be NP, which we earlier computed that it is the expectation of the binomial distribution. Okay, so once I have a moment generating function, I can generate higher order moments by taking higher order derivatives and substituting t by 0. So let us see moment generating function for the Poisson problem. So let x be a random variable whose PMF is a Poisson distribution with parameter lambda. The moment generating function is this. Okay, so again we take the PMF of Poisson with parameter lambda, and this is something we have to multiply with to create a moment generating function. So if we do again the simplification and so on, then we arrive here. So this is the moment generating function for the Poisson. Now if we again differentiate this with respect to t, then we get this. So recall calculus, how to differentiate this with respect to t, right? So this is like a chain rule. So so if I differentiate this, then e to the lambda e to the t minus 1, and then I have to differentiate the this part. Okay, so this part differentiation with respect to t will be just lambda et. So this is the differentiation, and if I set t equals to 0 here, then I get the expected value. So we know that for expected value for a Poisson random variable is lambda. Okay, so moment generating function can be used. So let us see if we could compute variance using moment generating function. So variance variance will be given by this, where it's double derivative. Double derivative. So we can do it like this. So double derivative of the moment generating function minus the first derivative squared. Okay, so so this is like if we do the double derivative, right? So if we do the double derivative, then so if we do the double derivative, then we get what expectance of x expected of x square, right? And then this is like expected of x whole square. Okay, so the variance was expectation of x square minus expectation of x whole square, right? This was the variance. Right. So we can prove this result, why the variance can be given like this. So I leave this as an exercise for you to figure this out. But what I would like to do next is to compute the variance for some of the distributions. Let us say binomial distribution. So I'm given this this moment generating function that so we have this moment generating function for the binomial, and then we have to compute this the variance. Okay, so if I have to compute the variance of the of this, right? So what do I need? I need so I need two things, right? So mx double derivative with respect to t. Okay, and so if we take the double derivative of this with respect to t, what do I get, right? So do I have a scratch space here? Okay, no, so I have to do it here. So if I take a double derivative, mx double derivative with respect of this, so this will be so if you take a derivative of this, so this will be n and n minus 1, and then e to the t p plus 1 minus p. So this remains, and then yeah, and then we have to take the, so the first thing would be let us do the let us write down the first derivative, because otherwise we did a first derivative here, right? Okay, let us see here. Okay, so this was our first derivative, right? So let us note down this first derivative, and then we can we need to do one more derivative of this. Okay, so sorry about that. Okay, so so I'm going to note down this because I did not copy this, right? So let us say the first derivative is given to us. So m prime xt is n et p plus 1 minus p n minus 1 p et. Okay, so if I note down this, then I should have noted this down here. Okay, so here I have this. Now I will do a lower derivative of this. So we recall that the first derivative of this is the following: mx prime t is n e t p plus 1 minus p n minus 1 p e t. Okay, now if we do double derivative of this, so we apply the product rule and the chain rule combined, right? So it's the product rule because t is, there is some function of t here and there is some function of t here. So we have to apply the product rule. So let us say this is so let us say this is our first function, right? So first function into derivative of the second, right? So into derivative of the second will be, so it's n minus 1 and e to the t p plus 1 minus p and then n minus 2. Okay, because there is n minus 1, so it now becomes n minus 2, and then there will be so if I take a derivative of this, right, so it's using chain rule, right? So you take derivative of this, then it will be PET only, right? So PET, one more PET will come, so this will be P square, and then this will be 2ET. And then we have to do the, so we did, this was our first function and this was our second. Okay, we are applying the product rule, right? Now so we did first function into derivative of the second, and then we take the second, and then we have to do the derivative of the first. So if we do this, then n e t p plus 1 minus p n minus 1, and then this is n p. So this is like just p e t only. Okay, so p e t. So overall, we have this. Now we have to evaluate this as 0, right? So if we evaluate this as at 0, then what do we get? If we evaluate this at 0, then we get n minus 1 and then p squared plus, because this becomes 1, right? So p squared plus np. So you can check that this, because yeah, because this will be like 1, and then this p and p gets cancelled, so we have n, and then this becomes 1, and then you get np there. Okay, and similarly here you get p square, this becomes 1, and so on. So variance we know is variance of x we know is m x 0 minus mx0 minus mx prime 0, and then squared of this, right? Because variance is expectance of x square minus expectance of x whole square. So this is what we have variance, right? So if we do this, and this we know was np, so this will become np squared, right? So if we do this, then this is n minus 1 p square plus np minus the expectance, which is np, and that is whole square. So this will be np and 1 minus p. Okay, so this will be the variance of the binomial using moment generating function. Okay. Okay, so we can also do variance of the Poisson. Okay, so if we do the variance of the Poisson, then moment generating function we have shown before. What is the moment generating function of a Poisson? So we have this. Now we need to differentiate this, right? So if we do the first differentiation of this m prime mx prime of t, right? So if we differentiate this with respect to t, right? So if we differentiate this with respect to t, what do we get? So this is of the form what? E to the sum ut, right? And this is your function ft, right? So if I differentiate this, then f differentiate this, right? So this is chain rule, right? Ut times u prime t, right? So if we do this, then what do we get? It is e to the lambda t minus 1 times, and then if I differentiate this, which is u, which is t here, right? So if I evaluate this at 0, so t will be 0 here, then what do I get? Oh, okay. I think if I differentiate this, then there will be lambda also, right? Because lambda is constant which will be there, right? So if I put 0 here, so this will be 1 minus 1, which will be 0, and e to the 0 will be 1, and this will be e to the 0 will be 1, so we will get lambda. So this is correct. We have seen that expectation of a Poisson is indeed lambda, and then what we need is mx double derivative this, right? So, but first we need to do, let us say, with the derivative. First we will compute. So if we compute this using the product rule, then we get lambda et minus 1 lambda et plus e to the lambda et minus 1 lambda et squared. Okay, so if I do apply the product rule, chain rule, all this, and at t equals to 0, what we get is this is lambda plus lambda squared. Okay, so from here the variance is mx double prime 0 minus mx prime 0 squared. So this is lambda plus lambda square minus the average squared, right? So this is lambda. So what we learn is that for Poisson, variance is also lambda. Okay, variance is also lambda. So now let us do some problems on random variables. I have done a few things about random variables, but it requires us to do some problems so that there is a good amount of clarity in working with random variables. Okay, so next what I will do is that I will do from here onwards I will only do some problems. So let us say this is the PMF of some random variable we don't know. Okay, the only thing important to check is that the sum should be 1, and which seems to be the case here. Now we have to answer the following: find the range of x. Okay, so what do you think is the range of x? So And then the next question is, let us say, find the probability that x is less than or equal to 0.5. Okay, so that could be another question. So these are the standard questions you may be asked in exams or assignments. Find the probability that x is between 0.25 and 0.75. Find the probability that x is 0.2 and x is less than, and given that x is less than 0.6. Okay, so this is the conditional. So let us see. Okay, so let us see how we can solve this problem. So the first question was find a range of x. Okay, so find a range of x. So range of x, if we go back and see what is the range of x. Range of x are the values taken by the random variable. So in this case, the values taken by random variable are 0.2, 0.4, 0.5, 0.8, and 1. So range of x, we know what it is, and it is 0.2, 0.4, 0.5, 0.8, and 1. So these were the range of x. And the second question was find the probability that x is less than or equal to 0.5. Right? So probability that x is less than or equal to 0.5. Okay, so probability that x is less than or equal to 0.5. So its equal is allowed. So we are going to consider this guy, and this guy, because for these guys x is greater than 0.5. Okay, so we will be restricted to now this, and then we have to compute the probability for this. So probability that this is less than or equal to 0.5 is the same thing as probability that x belongs to 0.2, 0.4, and since 0.5 is also included, I put this there. So, but this will be sum of the probabilities here, right? So this is probability that of 0.2 plus probability of 0.4 plus probability of 0.5, and this is nothing but probability that x equals to 0.2, probability that x equals to 0.4. In our notations, probability that x is equal to 0.5, and this is so if you read out so 0.2, 0.4, and 0.5, that is 0.1 plus 0.2 plus 0.2, which is 0.5. 0.1 plus 0.2 plus 0.2, which is 0.5. Okay, so now the next question for us was probability that 0.25 is less than x is less than 0.75. Okay, so this is same as probability that x belongs to 0.4 and 0.5, right? So 0.4, 0.25 and 0.75, right? So 0.25 range will cover this, and 0.75, so it will stop here. So the possible x that you have to consider now is 0.4 and 0.5. Okay, so 0.4 and 0.5. Now this will be equal to probability that x is equal to 0.4 plus probability that x is equal to 0.5. Okay, so if we do this, then it is 0.2 plus 0.2, which is equal to 0.4. Okay, and then the third question is find the probability that x is 0.2 given that x is less than 0.6, right? Probability that x is equal to 0.2 given that x is less than 0.6. Okay, so we apply the definition of the conditional probability that we know is that probability of x is equal to 0.2. Okay, and so the intersection is and, right? And probability that x is less than 0.6, this is 6, and then we divide this by probability that x is less than 0.6. So so what is this, right? So probability that x is equal to 0.2 and x is less than 0.6. So what is this? So x is less than 0.6. Okay, so x is less than 0.6 will cover these guys, right? So x is less than 0.6 will cover the values of x in 0.2, 0.4 and 0.5. And so this is for x less than 0.6, right? X less than 0.6. And another one is x is 0.2. So naturally the end will be just 0.2, right? So x is equal to 0.2. So x is equal to 0.2 will be just this. So if we intersect this, so this is the case x is equal to 0.2 and this is the case x less than 0.3. So if I take an intersection of these two events, then it will be just 0.2. So this will be probability that x is equal to 0.2 and denominator is probability that x is less than 0.6. Okay, so x is less than 0, so probability that x is equal to 0.2 is 0.1, so 0.1 and divided by probability that x less than 0.6. So x less than 0.6 are these three values added. So 0.1 plus 0.2 plus 0.2 is 0.5, right? It's like 0.5, right? So which turns out to be again like 0.2 is the answer. Okay, so I think we have done all four answers. Okay, so this is how you solve questions like this. These are standard questions that may be asked. Okay. So let us consider another problem. Let x and y be two random variables that denote the outcome of the roll of two dice. Then answer the following. So find the range of x. Find the range of x, range of y, and PMF of x and y, and find the probability that x equals to 2 and y is equal to 6, and find the probability that x greater than 3, y equals to 2, and let z is equal to x plus y, then find the range and PMF of z. Okay, what I will do is like I will skip this for the moment because I think it's similar to this except for the last point, which could be covered in other example. If I have time today, then I will come back to this. Okay, so let me go through some other interesting problems. So let us see this problem. Consider an exam that contains 20 MCQs. Okay, so multiple choice questions. Each question has 4 possible options. Okay, and assume that you can answer 10 questions correctly. Okay, assume that you can answer 10 questions correctly, but you are not sure about the other 10 questions. Okay, so there are 20 MCQs. You are sure about the 10 questions you can answer correctly, and you are not sure about the other 10, and you are going to answer them randomly. Okay, so assuming that there is no negative marking, so maybe you will answer them randomly. So let the random variable x denote the score on the exam, which is nothing but the total number of correct answer in this case. So find the PMF of x answer. Okay, so find the PMF of x and PMF and the probability that x is greater than 15. Okay, so this is the question. Okay, so now how we will solve problems like this using random variables. Okay, so let us define a random variable. So I'm going to solve this using random variables. Okay, so what I know is like the problem consists of like 2 parts, in the sense that one so the first 10 questions I can answer correctly, and then the other 10 I cannot. So randomness is there in the remaining 10 questions that I have to solve. So randomness is there, and X is the total number of correct answers. So X will in turn also become random, although the 10 questions are surety, but 10 questions are not sure. Okay, so overall X, which is the score that you get out of these 10, is also not sure. Okay, so what I can do is like I can take a separate random variable, okay, for this part, which will be Y. Okay, and it will be random because these are the ones that I am not sure about. And yeah, so then X will be like Y plus 10 and so on. Okay, and then these things will help because what I'm asking for is probability that I will get X greater than 15. So what does this suggest? So what does this suggest is 10 I am pretty sure. Okay, so 10 I am pretty sure. Now the question is, what is the probability that I get 5 or more correct out of 10? Okay, so what is the probability that I get greater than 5 answers correct here? So what we are expecting is that for Y, what I'm expecting is that it will behave like some it may behave like some random variable that I may be familiar with. Okay, so it's like asking it's like asking for 5 or more correct out of 10. Okay, 5 or more correct out of 10. So this may behave like some random variable that we are familiar with. Okay, so in that sense, yeah, so X will be some constant times some random variable that we may be familiar with. So this is how we will try to break our problem. So let us now formalize this. So let Y be the number of correct answer to the remaining. By remaining, I mean the ones that you are not sure about, remaining 10 MCQs. Okay, so and that you answer randomly. Okay, so that you answer randomly. It's like you have no hint at all. Okay, so you will answer completely randomly, and then this implies that X can be written as Y plus 10. So first goal for us is to find PMF of Y. Okay, so since this is an MCQ with 4 choices, choosing one out of the 4, your success rate it would be 1/4. Okay, so so what we have is, so I can use this space here. So for each question, success probability is 1/4. Okay, so hence we will perform 10 independent Bernoulli trials. Okay, so Bernoulli 1/4, because that will become the parameter for the Bernoulli, right? Bernoulli was like a coin toss with some unbiased, I mean the biased coin with probability of head is P and probability of tail is 1 minus P. So so in this case, your success or failure is there. So outcome is still one success or failure to answer a question. And to success probability is like 1/4, and hence the failure probability is 1 minus 1/4. So it is still a Bernoulli because if I'm focusing on one problem, then it's Bernoulli because its outcome is a success or failure. Okay, so it is immediately Bernoulli. But then I have like 10 questions to answer, so I may end up doing 10 Bernoulli. In other words, I may do one binomial with 10 trials, with probability 1 over 4. So both are equivalent, right? We have seen this before. So binomial is nothing but sum of the independent Bernoulli trials. So let us invoke those things here. Okay. So we perform 10 independent Bernoulli. So we perform 10 independent Bernoulli. Why 10? Because the 10 random questions are there, right? That you are not sure about. 10 independent Bernoulli with the parameter 1 over 4. Okay, that's the success probability trials. And y is the number of success, and y is the number of success that we have already pointed out before as well. So this will imply that y is nothing but actually binomial. So we have clubbed together 10 trials, and then the probability of success or failure is like 1 over 4. Okay, so the PMF. So sometimes we explicitly denote the subscript to say which random variable we are talking about, for which we are considering the PMF. So now binomial is like 10 choose y, and then 1 over 4. So p to the y, and then 1 minus p. The 1 minus p is 3 over 4 to be n minus y, which is in this case is 10 minus y. Okay, for y 0, 1, 2, 10. Okay, so there are 10 up to 10, and then it is 0 otherwise. So 0 otherwise. Okay, so far we have formulated our problem in a nice way. Okay, so we have come up to binomial. We need to find. We also need to find like PMF of x, right? So need to find PMF, because in the end we have to compute the probability that x is greater than 15. So PMF of x. So so we know that x is y plus 10. Okay, so the range of x that we will get, assuming that y is going from 0 to 10. Let us say the first 10, you reorder the problem, and let us say the first 10 is the one that you are not sure about. Okay, the first 10 questions are the one that you are not sure about. Should I take 0 here? Because then, or okay, I have to be careful here, right? Should I start with 0? I should not start with 0, right? I should start with 1. And then the remaining ones, yeah, or I start with 0, let us say. Then this I make it 9, okay? And then, so if that is the case, then 0 plus 10, right? So this is like this will start from 10, 11, and then so on up to, it will go up to 20, right? Okay, so so what is the PMF of x? PMF of x, let us say 10. So this will be probability that x is equal to 10. So this is the same thing as saying the probability that y plus 10 is equal to 10, and which is the same thing as saying that probability that y is equal to 0. Right. So this is the same thing as saying the probability that y, I should write capital Y here. Okay. So probability that y equal to 0. And this is something we know, right? So this is like 10 choose 0. We use the formula here. For 0, we know this, right? 1 over 4, 0, 3 over 4, and 10 minus 0. So if you compute this, then this will be 3 over 4, 10, because these guys will boil down to 1, right? So similarly, like I can compute probability of 11, which will be probability that y plus 10 is equal to 11. So this is probability that y is equal to 1, and this is 10, choose 1, and then 1 by 4, and then 1 by 4 to the 1 actually, and then 3 by 4, 3 by 4, and then 10 minus 1. If I'm using this formula here, y equals to 1, right? So this is like 10, 1/4, 3/4, and to the 9. Okay, so in general, we can compute probabilities. Okay, so let us continue from here. So in general, for the kth, okay, so this is like x, sorry. So for the kth outcome from which is nothing but probability that x is equal to k, which is nothing but probability that y plus 10 is equal to k, and this is nothing but probability that y is equal to k minus 10, will be 10, choose k minus 10, okay, and then 1/4 of k minus 10, and 3/4 of 20 minus k. Okay, so this is what we have. In general, this is the PMF. Basically, we have got the PMF of x, right? So to summarize, what we have is px k is 10, k minus 10, 1/4 k minus 10, 3/4 20 minus k equals 10, 11, 20, and 0 otherwise. Okay, so in order to calculate p greater than p of x greater than 15, okay, look, x below 10 we are not bothering about, right? Because that is the deterministic case, right? It's only random x greater than this. You may say, oh, okay, why don't you consider 0, 1, 2? Because x is like a score from 0 to 20, right? The maximum, I mean 0 to 19, let us say. So I mean 0 to 19 questions are there. Okay, so okay, the score. Okay, let's see. Okay. Okay, so I am sorry. So I think I was mistaken. So x was the total number of correct answers that we can give. Okay, so it can start from 0. Okay, so total number of correct answers 0 to 10. We have to remember that x is the total number of correct answers and y is also the total number of correct answers. So we have to include 0, and then so x can go from 0, 1 to in reality x can go from, and then 11, and it can go up to 20, right? So these are the possibilities. You may answer 0 questions and you may answer all. So but then up to 10 it's already deterministic. So this is the deterministic case. So I really don't bother here because it's a deterministic. So no longer random. X is no longer random until here. So I should focus only on up to this point, right? So this is why you see it is enough for us to start from like yeah, from here, right? Now what do we have? So in order to calculate p greater than probability that x is greater than 15, right, what should we do? So we should consider y to be, so for this to happen we must have y to be 6, 7, 8, 9, 10, because we have to add up, because up to 10 is guaranteed, and then I must have y either 6 or 7 or 8 or 9 or 10. Okay, then only it will be greater than 15. So this is what we have. So so for these values, what is the for these values we have we know the y values, right? So 10y 1/4 of y, like this is the binomial that we wrote before. 3/4 10 minus y, okay, and then y is 6, 7 up to 10, and it is 0 otherwise. And then probability of x for these y values can be computed now as 10k minus 10 and 1/4. Well, I'm just repeating in some sense, but what I'm trying to say here is things now boil down to this only. Okay, so 16, because I need only probability values for this 16 onward. So do I have a scratch space? Okay, maybe I will use this scratch space, because although this is for problem 4, so probability that x is greater than 15 is probability that x is 16 plus probability of 17 plus ... plus probability of 20. Okay, so now we have the PMF. Once we have the PMF, then we can plug in these values. So this is like 10, 6, 1/4, 6, and 3/4, 3/4, 4. Okay, so probability of we read this out from here. Okay, we have written this down here, and then we just do this. We just plug in this. You don't even have to like explicitly compute these things in the exam. You just keep your answers. You can keep your answers like this. It is enough. Okay, so this will be the answer to this problem. Okay, so we have seen that the problem like this can be solved by random variables, and then you have to identify what are the deterministic cases, what are non-deterministic cases, random cases. The random cases you have to, if you can deal with it separately by introducing a random variable. So in this case, we introduced a random variable y, and once I introduced a random variable y, then the next step for me was to figure out which distribution it belongs to. So in this case, I could figure out that the outcomes are like success or failure to answer a question, but then it was a bias. So it was 1/4 of success and 3/4 failure. So this went into binomial, but then I realized that there are 10 random questions, 10 questions that you're going to answer randomly. So it will be like a 10 binomial. And I know that each question is independent of each other. Okay, so one question, one random question doesn't influence the other random question. So then we realized that it's nothing but sequence of Bernoulli is nothing but binomial. So then we got binomial 10, 1/4. Okay, so remember, yeah, so 10, 1/4, and then like sometimes you may flip what is success and what is failure and so on. Okay, so it could be I mean, you could have taken like binomial 10 and then 3/4, right? So okay, so once we have that, we have the binomial, and then the remaining thing that is needed is to find the PMF. Okay, so we found the PMF, and PMF, since as I said, these are the templates that we have developed before for binomial. So binomial PMF we knew. Now the only thing that was remaining was to identify PMF where x is greater than 15, and that is something we did by looking at those cases where we have x greater than equal to 15, which is this case. I mean this case here. So these are the, so we got the PMF for these cases which are of interest to us, and once we have that, then we we could compute the probability, required probability. Right. So let us do more practice. So let us see, this is another problem. So average number of customers arriving at a grocery store per hour is 10. Let X denote the number of customers arriving from 10 a.m. to 11:30 a.m. Okay, so 10 a.m. to 11:30 a.m. and the question is, what is the probability that the number of customers arriving in this time will be between 10 and 15. Okay, so this seems to be Poisson because average number is given to us and there is a time involved here and average is given to us. So this seems to be a classical case of a Poisson, and indeed it is. So, and what we are looking at is the interval also. So what we are looking at is interval of the duration. How much? 1.5, right? So 1.5 hour. So this is the duration we have. So this is a classic case of a Poisson, and then but since we are looking at the duration of 1.5, we have to scale our average accordingly. Okay, so because the average that is given is for per hour, which is 10. So we have to scale this by multiplying it by 1.5 so that we get an average for the, we get the average for the required time duration. Okay, so this is something, these are the cosmetic things we have to do for Poisson. Okay, so let's see this. So we have interval of length 1.5 hours. So this implies, so the number of customers in this interval will be following the Poisson, but lambda will be 1.5 times the average, which will be 15. Okay, so now we can invoke okay, so I have only this page left. Okay, so we can invoke thus this implies probability of 10 less than x less than 15 is sum of k equals to 11 to 15, and this is the PMF of the Poisson, which is nothing but k equals to 11 to 15 and e to the minus 15 times 15 to the k by k factorial. So if you do this sum and so on, basically you can stop here. We are not checking your algebra skills, but just the probability skills. So this is essentially the answer. One can put in all the values and get the answer. So what do we learn from this problem? The problem looked like a Poisson, okay, and average was given for some time interval it was given. But then we found that the random variable that we were given had a different time interval than the time interval for which the average was given to us. So time interval for the random variable was 1.5 hour. So we scaled our average. So remember that this is something you should not forget. Okay, you need to scale your Poisson random average accordingly, according to the random variable intervals. So once you do that, then after that it's a straightforward thing. You have to compute probability that x greater than 10. Since x is greater than 10, I have to start from 11. And since it includes 15, I have 15 included here. And then these are we have to like sum this up. Okay, These are like mutually exclusive events. So we sum this up and then we get the answer. Okay. So this will be all. I will discuss problems again also in the next class, just to make sure that you have some good hold of the random variable. So I guess with this, I can stop. Okay. Thanks and bye.